Hey everyone, GM to everyone that's watching via recording or that's joining right now. Um, I'm here with Salil. We're doing our last workshop on Noir for NoirHack, and this will be on StealthNote. So StealthNote is having a bit of a viral moment right now with a couple of media outlets picking up what Salil has been working on. So in this workshop, we'll learn a bit more about what it is. And then we also, if time allows, we'll dive into another Noir app, Gitclaim. So I'll pass it to Salil to kick us off for this workshop.
Yeah, thank you, Rafi. Let me start by sharing the screen. Yeah, yeah, I think this is enough. Uh, you can see the browser, right?
Yes, yeah.
Yeah. Sorry. Yeah. So this is like a workshop on how StealthNote is built. Yeah, then don't think of it like a presentation. I'll just be doing a demo uh, code walkthrough and then like explaining how it works underneath, so that you can build similar applications. And StealthNote is powered by some Noir libraries, like the core proof generation part of the Noir. I mean, the core code of the Noir circuit. That's like a library, the JWT library. So we'll go through that as well. But yeah, don't think of this as a pure presentation. Like it would be more useful to you if you engage. Like I mean, if you have any questions, you can stop me anytime. You can send in the Q&A or in the chat, and then I can stop, and then we can go through your questions. Yeah, so let's get started. So StealthNote is like a application. It's like kind of like a social media application where you can send anonymous messages, but proving you're part of the company without revealing any personal information. So you prove that you work in some company, but you don't reveal your email or name, and you can send the messages. And like every other user that's using the application will know that this message came from someone within the company, but not exactly which person. And this works using like something called JWT. It's like when you sign in with Google with your company account. We are using ZK, zero knowledge proofs, to prove that you own a company account, but then we don't reveal your name or email address. And that's like the essence of it. We'll get into the technical details, but I think we can start with a demo. So the URL is this one, stealthnode.xyz. I'll just send it in the chat as well. You can try if you have a company Google account. Like if you scroll through it, like all of these messages came from different teams: Stacker, Horizon Labs, PSC. This is Aztec, and then you have like a verify button against each message to verify the authenticity. And sorry, you can send a message by proving you own a Google account. So at this moment, it's only possible for companies that use Google Workspace for the emails. So if I click this, I mean, we use Google Desktop. I mean, it's already signed in, so you saw the pop-up and it disappeared because I'm already signed in with my Aztec account. And then it's generating a proof, which will take like 10 to 20 seconds. Prove that I have a Google account with this domain, azteclabs.com. And now I can send anything, and then it will appear here. Yeah, I mean, I don't want to send another spam message, but you can try with your account. Yeah. So there is also like an internal chat where the messages you send are only visible to people in your company, and like this is the general feed. And yeah, there are a couple other features like liking here, and then if a message get like more than a couple of likes, like then it get cross posted to a Twitter account. Yeah, so that's all that. But yeah, we can look into how you can build such an application. So I'll go through from the beginning, like what's the first version. This may be like the second or third iteration, but yeah, we can go through it step by step. Like what I mean is like this is like a very optimized version of the circuit and like the application. But yeah, we'll start with the beginning basics and then get the. Okay, so what happens here is like as a first step, like when you sign in with Google returns something called JWT, it's JSON Web Token. It's like a token, which is the image, I mean the JSON payload you see here, right? That is the JWT. It's not like something Google created. It's like a standard. It's not something Google created for doing ZK or anything. It's primarily created for authentication purpose. Like even Web2 applications use this. So like if you're signing into a traditional Web2 app and you sign with Google, that application can receive this data from Google. So it contains the name, your email address, yeah, some other data, some extra data, and like there's a nonce, it's like a random number, there's the expiry date, and like this is issued by Google. And usually applications use to verify a Google account, and this is kind of what happens when you sign with Google in other applications. But this JWT, the structure is like this. There's a headers and there's a payload and a signature. And it's a string that concatenates this header, payload, and signature, and then join them with a dot. So it's just a string. So when you sign with Google, Google will send you a string that has 3 parts. And this is a standard, it's not a Google thing. You can do the same with Microsoft or pretty much like any OAuth 2.0 system that uses OpenID. But yeah, the headers is like a JSON. I mean, in this image it's hidden, but what it says here, like what is the protocol used for this signature, like RSA, and what's the hash mechanism. So usually almost all JWTs, they have the SHA-256 and RSA. What it means is like that the issuer, in this case the Google, they will take the headers and the payload, which contains all the personal information about you. They take a hash of it using SHA-256, and then they sign that message. And that signature is also included here. So if I sign in and I get this JWT, then I can send it to anyone and then let them know that I have a valid Google account and with this email address. I'll have to send them in their data. And what they can do is they can take the hash of the headers and payload, and then they can verify this RSA signature with Google's public key. So Google will host their public key in some URL. I don't know. Yeah, maybe. I mean, if you search for it, you'll get like the public key that Google used to. I mean, the private key that Google used a private key to sign this message, and the corresponding public key they make it public, and it will be in some URL in their domain. And anyone can download that public key and then verify this signature. So yeah, anyone can verify the authenticity of their data by verifying the JWT signature with Google's public key. So there is no ZK here. I think it's just the traditional Web2 system. But you already saw one problem here. Like, in order to convince someone that I have this account, I have to share this and their data. So like in the payload, you have the name and you have the full email address. So basically, there is no privacy here. But yeah, you can still get the authenticity. Okay, so that's the first building block. JWTs contain this data and the signature. So no ZK. And like another thing we can do is, this should be here. Okay, so in the JWT you saw this nonce parameter, right? So this is some random value that the application, like in this case StealthNote or whatever application that's triggering the overflow, they can set it to a random value, and then that value will be included in the signature. So when you click this button, like it's sending like a random value to Google, and then that same random value will be included as a nonce. And like originally it was meant for as an additional security measure for websites to ensure that like the signature was meant for them. But yeah, we'll be using it for some other purpose. But with this property, we can have Google sign arbitrary information, right? So let's say in case of StealthNote, you are posting a message, right? Maybe you can put the hash of the message as the nonce, and then you sign in with Google, and when it returns, it basically means that it's like a proof that this same person, the same person also sent the message, because the hash of that message is included as a nonce. So yeah, that's a building block we need. Okay, so yeah, so like I said, like you can still do that. So if you have a message and you take the hash of it, and then you sign with Google, and then you post this message in a server, and then like anyone can verify the message came from this person. Just that there is no privacy, there's no, I mean, you will be still revealing your full email address, but yeah, everyone can make sure that the message came from this person, and this person is in this particular company. Okay, but yeah, I mean, the problem is that we are revealing the email and the name, and that's exactly what we are solving the ZK circuit. And the idea here is to have like a known circuit. And in the circuit, we will verify the RSA signature is valid, and we'll also verify the nonce claim is valid. In this case, we'll just verify that the nonce is the hash of the message, like we planned. Yeah, and then we extract the email claim. Oh, sorry, by claim, I mean these fields in the payload. These are called claims. Basically, it's a key value pair in the JSON, but yeah, in JWT sense, it's called claim. So yeah, you extract the email claim, and from the email, you extract the domain and make the domain public. And this is what happens in the ZK circuit. Okay, so if you were to send this payload and the signature directly to a verifier, or like anyone, in this case, in case of the StealthNote, the verifier basically means other people who are using the application, right? So this message is sent from someone in Ethereum org, and I want to verify this, so I'm the verifier. So this message and a corresponding ZK proof is hosted in the StealthNote server, and then it's sending me that proof, and then I can verify. Yeah, so if you send this message and this whole payload, anyone can verify, but no privacy. But the same thing happens with the ZK circuit. So what they do to verify this, I mean, if you're sending the whole payload, what the verifier will do is to run the RSA verification of the signature, right? You will take the hash of you will take the hash of headers and payload, and then verify the signature with Google's public key. And you can do the same thing in ZK circuit. And as a user, as the message poster, you do that. You prove in a ZK circuit that the RSA is valid, and do all these steps, and then they send the proof to other users. And then instead of like verifying the RSA signature, they can just verify the ZK proof and get the same guarantees of like verifying the RSA signature themselves. And in doing so, like the email and other email and other inputs remain private, and only the domain is made public. And that's the benefit of like using the ZK circuit here. It gives you privacy. Okay, so we discussed like using hash of the message as the nonce, but the problem is that a new proof, I mean, if you just do that, you will need a new proof per message, right? So every time you send a message, you will have to take the hash of the message, use that as a nonce, and then sign into Google, and then generate the proof. So this is not a great UX. Proof generation takes like 10 to 20 seconds. Then you need to do the whole sign-in flow for every message. It's a bit pain. But yeah, a solution to that is to have like a ephemeral or like temporary key pair to sign messages. So what happens is here, like when a new user come, you generate like a key pair, private key and public key, and save that in the browser local storage. And the public key of that key pair, you sign with Google as the nonce. And then with that proof, and with your private key, with your local temporary private key, you can sign any number of messages. Okay, so in this case, the verifier is verifying that the message was signed by some public key, and that public key was part of a JWT in the nodes. So you get the same guarantees as before, but you don't need to generate a proof per message, and that's like another level of optimization, or like UX improvement. Yeah, but probably this is that the messages you send with same key pair, they are connected. So let me sign in again. Yeah, so this time it will generate a new private key, public key for myself. It will be saved in the local storage, I think. Yeah, so this is the private key, public key, and expiry. It's generated here, and then this public key, the hash of it, that is used as nonce, and then I can send any number of messages from here. But all these messages I send, that will be connected. They will be connected. I mean, anyone verifying this proof, they know it came from the same person, because those messages, like all these messages, are signed by the same public key. But the solution is that to allow users to generate a new key pair or new proof anytime they want. So yeah, I can click this button and it will generate a new key pair and then create a new proof. And then the messages from then onwards, it will be using a it will have a new public key, new private key that signs the message. So those messages won't be connected. Yeah. Okay. So yeah, another problem we have is privacy from Google. And this is not an entirely solved problem, but with the current design, with whatever we have discussed so far, we are setting the nonce as the pub key, right? And then like anyone verifying this proof, they will receive the public key with which this message was signed. So Google can find out which person signed a message, which person sent a message, in this design, like in whatever we discussed so far, because Google has access to this public key, and then they will also have all auth logs, right? All signing with Google logs, and then they can cross check against that and find out which person has this public key. So the solution is to directly use the public key when you as the nonce, but you can use something like hash of ephemeral key and then assault. So you just had assault, so Google can find out your actual public key, but in the circuit you can prove you own the public key. So the circuit is something like this. You have the JWT header and payload. This is the signed data. And then you have the JWT public key, which is the Google's public key and the signature. And then you have your public key, which is a public input to the circuit. This is something that, the key that was randomly generated. And then you added a salt when you hash, right? That remains private. And then you have a domain like the company that you belongs to, and that's also public. And in the circuit, we are verifying that we take the hash of JWT header and payload, and then we verify RSA. We verify that the message hash is signed with when signed with this public key, you will get the signature. And then we also verify that the hash of your public key plus salt is the nonce, right? And the final step, this is the important bit. By up to this step, you are verifying everything. The JWT is valid and public is valid, and then we do another step to make sure the domain that was passed, which is a public input, contained in the email, and like specifically after the character. So yeah, so when you generate a proof with this circuit and then give this proof to someone, like what's public is your public key and then the domain, and then you're sending the message. Yeah, we'll get to that. We'll get to the whole flow, but yeah, this is how the circuit works. Let me go through some of the questions. In private dashboard, anyone can also verify the message, or is it only in public? Yeah, in private also you can verify the message, but yeah, those messages are only visible to people in the same company. So yeah, folks in your company can verify. It's not like cryptographically private or encrypted. It's just hidden from the public field. So there is no like fancy cryptography to hide from rest of the world. This is just private at the courtesy of the server. So yeah, it's just hidden from the public field. Yeah, I see a few people raising hands. Rafi, I don't know how
Oh, I
the
just asked them if they are building with ZK and so they just said that they are.
oh yeah, okay, cool, nice, yeah. Yeah, so we can continue, right?
Yes, for sure.
Yeah, we can do a code walkthrough. Just use GitHub. Yeah, let me make it bigger. Okay, so I think we'll just go through the Noir circuit part, and this is the circuit, and you can see it's dependent on one library, the JWT library. Yeah, I think it's no longer in this URL. It was moved to the ZK email org. But yeah, I'll share this in the chat. Yeah. Okay, so maybe it's better to start with the library and see what's happening underneath. Okay, so StealthNote depends on this library. So we're going through the JWT library first. Yeah, so yeah, in this one, like you can construct the JWT structure, or maybe it's better to start from here. Sorry. Yeah, we discussed the circuit structure already, right? So this is the StealthNote circuit, and then you have the data. This is I mean, this is something we haven't discussed, but yeah, let's keep that aside. But yeah, you have the JWT public key, signature, domain, your ephemeral key, the salt, the expiry. Yeah, and then we are creating this JWT object and calling it .verify, and this is like powered by the JWT library. We'll get into that, and then in the next step, from the JWT structure, we are calling the Gitclaim string, just like get the string with key nonce, and then you will get the value here. Yeah, so you're converting that into into a number, into a field. Basically, it's a number. So you just so this is the hash of the nonce will be the hash of the message, right? Hash of the public key and the salt, right? So we're getting that from the JWT payload. What this step is doing is in the key value pair in the JSON structure, the value will be like a string of like a large number. So we're just converting that into into numeric form. Okay, and you have that, you keep that aside, and then you're doing the Poseidon hash of the inputs, ephemeral, public key, the salt, and the expiry, and we are verifying that it's the same as the nonce field. So we are just validating the public key input here. When hashed, the salt and expiry returns the same value as in the nonce. And if this fails, you cannot generate the proof. That's what the statement is doing. Then we are also asserting, in JWT, we are asserting another claim called email verified, and the value should be true. Okay, so this is like if you create a Google account and you don't verify, then you don't really have a Google account. I think, yeah, so I mean, it's part of, it's like another, yeah, you see this key, right? Email verified true. So we are just making sure the value is true. Now you're getting the email claim. So get claim string email, and you'll get the email value. And from the email, you're extracting the domain. So there is like this utility function for that. You're looking for this key, and once you find that index, the domain start index, you're validating that every character after that in the email after that index is the same as the domain. that you passed in. So there is a public input domain. You're making sure the characters of this domain is same as the value after the add character in the email claim. So yeah, once you finish that, like once you meet all the assertions, then you can generate a proof out of it. So we can get into, so the part I skipped is this partial data, right? It's something called partial SHA hashing. It's might be like a bit advanced topic, but okay. So one second, yeah. So we have this step, right? Like the first step to verify our signature is like take the hash of the header and payload, and this is like an SHA hash is an expensive operation to do in circuit, because yeah, I mean expensive as in it takes a lot of gates, so it takes more time to generate a proof of that. Like especially if your input size is big, then the proving time will be very high, because SHA takes up too much gates. Because SHA is not something designed to run efficiently in a ZK circuit. So what we do is, but the good thing is like the SHA hashing there happens in sequence of like 64 I think like fatal bits, but it happens in sequence of certain bits. So you can hash a portion of SHA outside the circuit and then pass that intermediate hash, the partial hash. Yeah, I mean this. I can share some links if you want to read on this, but yeah, basically what happens is like this input is like a hash of the your payload up to certain index, and this data, that's the remaining data, and then you can do the full hash in the circuit from this intermediate result. The only catch is that you can only extract data from the you can only extract claims from the data that's included in this partial data, like the data that's being hashed in circuit. But yeah, that's like a I mean, if you don't understand it now, it's okay. You can just think of it like a regular SHA hash. Yeah, we can go through the, oh, sorry, there's a question. Why we need to use unconstrained function? Why not without? Oh, so I think you're referring to this one, right? Yeah, here. So this is unconstrained because I wanted to use this break statement. Like, so it can be like a, so you can think of unconstrained function as a input to the circuit. So what we're trying to find out here is what's the index of the domain in the email. So the email is like something at domain.com, right? At which index the domain is starting. You can pass that as an input, but or you can just write an unconstrained function and then loop through the email, look for this character, and then that character that index plus one is the domain start index. But either way, even if it's input or it's unconstrained, you are constraining it later, because you are validating from that index the domain is present, and you are also validating the value. I mean, from that index, the value before that index is 64 is ASCII character for this one. So yeah, this one doesn't have to be constrained. I mean, it can be even like you can remove all of this and then you can just pass the domain start index as a private input. That can also work. Okay. Sorry. Yeah, so in generability library, that's what the main thing is happening. Like you have this init function with data, and then you like it's basically returning the structure, this struct. And then like I think the interesting bit is the verify method. So yeah, you are, so if it's a hash, like you're doing like the SHA hash of the payload, and then we're calling the verify. This is the RSA. Okay, so this came from, if you scroll to the top, this came from the RSA library. So you're just like verifying the RSA. You're doing the SHA hash first, and then you are verifying the RSA signature. And like there are all these utility methods like get claim string, assert claim string, and then for numbers, 4 booleans, and they're all internally calls this function called Gitclaim, which is making use of the Noir string search library, and then it search that key is present. Yeah, it looks for like a key, the JSON key is present in the payload, and then if it's present, then we'll get the position, and the next character should be a colon, and then all the value, like the value is all the characters until the next line or comma. So you set all those and then return the value. I think it's you can it's common there, so you can go through it. All these extra statements is to distinguish between a string character and a numeric characters, because like string values are surrounded by codes and numbers are not. But yeah, that's the it makes use of the string search library. So we can use the RSA library to verify the signature, then SHA to hash. There is a base 64. Oh, I think I missed this part. So sorry. So we need base 64 because what is actually signed is the base 64 encoded headers dot base 64 encoded payload, and that is what is signed with SHA-256. It's not the JSON exactly. So you need to do a base 64 decode in the circuit, which will be somewhere in here. Yeah. So yeah, I think it's in this prepare hashtag. So we are using the base 64 library to decode the data. Yeah, and the string source library is to search for the JSON claims, and we have the big num library to basically because the RSA signature is 2048 bits, and in the circuit you can have only up to 253 bits because of the prime field used in the backend. So yeah, the public key, for example, and the signature, you are sending it as chunks of, you split them into 18 limbs of U128. So yeah, to do operations on that, you need a big num. But yeah, that's you can go through this, and like if there are any questions, you can ask in Discord. But yeah, using the library should be relatively easy. Like in StealthNote, you can see how it's used, right? So it's basically this one. You need only this, and then you can do assertions and you can get claims. There should be some examples in the README. Yeah, you pass these details, and then you can you can get call this verify on this method. And to generate the inputs, there is like a JS SDK. Here it's also published to npm. By generate inputs, I mean you can pass a JWT. Should be here. Yeah, so in your JS you can use this package and then call this method. So you can pass the JWT string, right, like the full string that you get from Google, and the public key, and then it will generate the inputs that you can pass to circuit. So it will generate the values for all of this. So it's very easy to use. And in StealthNote, I think we can probably find that here somewhere. Yeah, so this is the Google generate proof. We load the Google script and then open the sign. So this method, there are functions here below, like in this file, in Google Auth file. We open the pop-up, or like there is something called Google One tab, just like it appears here. And then you are sending this to you are sending the user to this URL, and then when it returns, you get the token, you get the JWT, and then you are generating proof, and with this helper file here for the JWT, and it's using this generate input from durability method. So this is what ID token, that is what is returned from Google. And then once you have the inputs, you are calling the circuit. So it will generate the input, and then you're preparing this object with the extra information, like the domain. And then this is the standard Noir proving, like you are importing the backend, and then you call the backend.generate proof, and it will give you the proof. Yeah, we can see what happens in the full flow. So it's like a lot of text here, but yeah, let's try to go through this. Like when a new user comes, we generate a temporary key pair, and then use the public key as the nonce and complete the overflow. We'll create a proof, and then we're sending this public key and proof to a server. The server verifies the proof and then save it in a database. Okay, so StealthNote has a server. There are no trust assumptions on the server. Server is like a database. But yeah, this is Next.js. So you can see the API here and membership. This is the thing we just discussed. Yeah, so a post method on this calls this one create membership. So you're receiving the proof and the public key. I mean, you're also getting the expiry date and everything, but yeah, these two are the key. And it saves in the database. And when sending a message, users sign the message with their ephemeral private key and send that to the server. Now, server verifies that the corresponding public key to this message that exists in the database, which means that like it was previously registered, and then verifies the message signature and then save that in the database. Yeah, when other people come to this website, they see all the messages, and they also get the message signature signed by the temporary private key, and like they'll get the public key, and then also the proof that the public key was signed with a durability proof. Okay, so yeah, that's how what is happening. Sorry. Yeah, man. So StealthNote, like the application is kind of generic. You can see we're calling it something like provider. If you go to the lib, and Google is like one of the proof providers. So we can add more stuffs here, like you can prove you're living in a city or country using ZK passport, and you can use ZK email to prove many other things. Like maybe you can prove you went to an event, or you got accepted into Y Combinator because like you received an email from them. So in general, StealthNote is like a like a platform for so like sharing anonymous message by proving you're part of any unknown group. You just need to have a circuit for that. Yeah, so I think I'm planning to add more stuff here. Okay, so with the current company JWT proof, like one issue or like the trust assumption, this is like something important. Like when you're designing the application, you need to yeah, go through like the trust assumptions and like maybe disclose that to users. So in the disclaimer, you can say some of the assumption. And what it means is like if you are like the only person from the company that use this app, and then you're signing in with Google, right? So Google will have a list of everyone who used StealthNote. They cannot like link a person with a message, but if it's only one person from the company who used it, then Google will know which person is that, and maybe your company can like ask Google for that information, and then they can find out who you are. So in general, like the more people in a company use this app, like the better than it is. Another issue is like if you sign in now and then Google knows you signed in now, and then you immediately send a message, then like the time of the message and the time of someone logging in from this company, maybe they can correlate them, and then probabilistically, I mean, they cannot definitely prove that it's the same person, but yeah, like with some probability, they can do some guesswork. So a different solution to this would be using ZK email to prove that you have received an email from the company, or like you can send an email on behalf of the company. So you don't use the Google flow, but yeah, it's like a balance of better privacy and the UX. I think like the ZK email flow, the UX of that it wouldn't be that great. Like it won't work in mobile. You'll have to, download an email and then drop the EML file here somewhere. But yeah, this is something I'm planning to add, and like give users the option to choose from, better privacy or like easier UX. So depending on the message you want to send, you can choose either of that. Okay, I think yeah, that's all I wanted to talk on StealthNote. Is there like any questions on what we discussed so far? Okay, I don't see anything. Okay, so we'll just continue. So we briefly discuss the email. So yeah, I wanted to also so the idea, the goal of this was to, like give some overview on how this is built, so you can build similar application. So you can use like maybe like even the same proof of being in a company. You can build something like Glassdoor or like the levels FYI, like the salary portal. I mean, there is no way to prove that the messages you send or like the salaries you post are authentic. It's just you can only prove you are from the company, but no guarantees on the message. Yeah, with that limitations, you can build similar applications. I mean, underneath they all will be using the same infra, but the goal is to build applications, right? Like products, so something that people can, even outside of ZK or crypto space, can use. So yeah, you can build like a Glassdoor or something with same underlying circuits and code, but like a totally different UI. That's still possible. Yeah. On that note, I wanted to go through ZK email and like some example apps you can build with it. Yeah, I think there was a workshop on ZK email like 2 or 3 days back. So if you haven't seen that, you should check that. Um, um, yeah. So there is a question. Would you explain the timing attack again? Yeah. So okay. So that by that I mean like, so now I'm signing in with Google, and oh, so you see the pop-up up here. Like, no, I mean it's doing a Google login, so Google will know I logged in now. And if I send a message immediately, and then Google see a message like this here, someone from Aztec said, send this message, they can check the time of that message, and then they can find, they can look for auth logins around the same time, and then like, say it's the same person. And Google cannot prove that it's the same person as long as there is like more than one person from the company. But like, yeah, they can like probabilistically say it's probably the same person. But yeah, it's not. I mean, there cannot be any proof it's the same person. Yeah, I don't know if it's calling it timing attack is the right word, but yeah. Okay, cool. Yeah, so what's the ZK email workshop? I think they get into more detail, but yeah, on a high level, it's kind of similar to JWTs in the sense that it's using the SHA and RSS signature. So every email, pretty much every email that you receive and send today, it's signed by the email server. So if you're sending an email from your Gmail, then Google is signing it for you if you don't notice this. But yeah, if you have a company mail server, then usually the company team, they set up this DKIM signature. And what it is like, it's like there is a signature in the email. So email have, I don't know if I can open an email. Yeah, we'll probably open an email and see that later. But yeah, every emails have like this thing called headers, and in the header there is like a key called DKM, which is like the signature for the email. It's kind of like jailbreak, but in like the signature is on some of these values, like the from address to address subject and the hash of the body. You take a hash of it and then you sign, you do a RSS signature with your private key. I mean, this is the email server doing it. and the public key for this is shared in the DNS. Yeah, I think like the ZK email workshop, they will be going into detail. Okay, so what it means is like when you receive an email, you can look for the signature, and then if email came from someone at azteclabs.com, you can query Aztec Labs DNS for a particular DNS key, and then you will receive the public key. You will receive Aztec's DK and public key. And then with that public key, you can take the hash of the email and verify the signature and make sure the email is authentic. So this was originally introduced to, like verify the authenticity. I mean, this is like a very old protocol. It has been there for some time. And like in case the signature doesn't match, like the your email client will generally put it into spam. Yeah, so that's why like DKIM is useful. But in our case, we can use this to make proofs of email. So just like the RSA we had in JLPT, we can verify the email RSA in circuit, and then you can keep the subject body or two hidden, and you can only reveal your from address, or you can only reveal the domain, or only the subject. So depending on your use case, you can selectively reveal the information you want. So there is a Noir library for ZK email, which you can use to build. Let me send this as well. Yeah, which you can use to build ZK email apps. Yeah, you'll be in your circuit, you'll be adding this library, and then this is how you would use it. And there is also like a JS SDK here, which you can use to generate the inputs. So I have this one application that was built with ZK email. So let me share that. So that's what we will briefly go through it today. And like this is the URL. Like it's you can try it probably. Yeah, this is the URL. So it's called Gitclaim. It's like an example app to claim airdrops by proving you contributed to some GitHub repository, but like without revealing any data, like your email address or anything on chain. So yeah, what I mean, so it's asking for drag the EML file here. So if you're in Gmail, you can like against every email there's a download option, so it just downloads as a EML file. So you can download emails pretty much in any email client. Yeah, so this is one such email I downloaded, and you see this is like I don't know if it's big enough, but yeah, it's a email from GitHub saying like one of my PR was merged, and yeah, I'm on Mac. This is like the email I downloaded from the Apple mail client. But yeah, so we'll just attach this. Open. Okay, so yeah, it parsed the email. This is the repo name. This is the PR number. Email. This is private input. The public input is the repo. And then yeah, I just need to put my Ethereum wallet address here. But yeah, just keep. I mean, it's not even a valid address, but yeah, let's use that, and you can generate a proof. Yeah, while that is done, we can go through the application. So the circuit is here. Okay, so it's depending on ZK email library and string search. And in our circuit, yeah, you have all this input. The only public input is the repo name. And this header here means the email header, and the body, and the public key, signature, repo, PR number, email address, and your Ethereum wallet address. Yeah, I think this should have been a public input, but yeah. So we're just like verifying the length. Wallet address is 160, just making sure it's a valid Ethereum address. And then you're calling this verify DKM. This is coming from the ZK email library. So you're just verifying the email. So email verification is done here. And then you're getting the body hash you're verifying the body is also valid. Again, this method are also coming from Gitclaim. Yeah, it's here. And if you go through Gitclaim usage, this will be mentioned. And like there are some examples here. Yeah, extract address, verify. Yeah, maybe this one. So it's just like the standard code to verify the. It's like a copy paste of this, I think. Okay, so yeah, so you verify the email, you verify the email body, and at this point, we have verified the email body, and then we are using the string search library to. So this is the utility function. So we are just like verifying the in the body we are looking for like we are validating the it's a pull request merge, like the peer URL you pass that's present in there. Then we're also asserting that a specific string is present in the body. So if you go here, yeah, you see this message, right? Like because you author the thread. So the email the Google sent GitHub send you when you merge a PR, it will contain this this particular string. And that's like a unique thing to distinguish such email. So one second. Yeah, so when you're building with CK I think the task is to find unique emails which you can make very interesting proof. So if I just take any email from Google, sorry, any email from GitHub that has the word merged, that won't be enough, because like when a PR is merged, other people who review the PR, they also get a notification, right? So you need to make sure the email contains the merged word, plus it's also like addressed to the same person who opened the PR. And just by observation, um, yeah, if you are the person who opened it will have this particular string. You are receiving this because you authored the thread. But yeah, if you review the PR and the other person merge the PR, and you will receive an email saying the PR is merged, but it will not have this text. So yeah, when you are building this email, the you need to identify like unique emails to make interesting proofs of. Okay, so yeah, I mean, if you go through this section, like in the README, it explains everything. Yeah, this is, I mean, this is not intended to be like a real airdrop applications or not a production ready thing. It's like a proof of concept example app, and it goes through concept of nullifiers. Nullifier means like you don't want one person to be claiming the airdrop multiple times. So you need to generate some unique value from the email that corresponds to this person. And then in your airdrop smart contract, you save that nullifier. So if you see that again, you will reject that. So what can be like a good nullifier? You can use the email address, but then you don't want to reveal the email address on chain. So there are things like that. Yeah, so you can go through this. Yeah, our proof is here. Like there is proof and there is public inputs. You can click this button. It's not implemented, I think, but yeah, you can verify our proofs on chain, right? So you can send this proof on chain, and yeah, if it's valid, you can send some rewards to this token. So I think that part is not implemented, but yeah, you can verify proofs on chain.
Awesome. So Leo, I
Okay.
have like maybe a few questions for you just around helping beginners figuring out how to build.
Yep.
Um,
Mhm.
Really quick, maybe so based off your experience with StealthNote and Gitclaim, maybe what are some common mistakes or maybe misconceptions that people encounter either with these projects or just in general with Noir? And then maybe you could also share any particular resources or libraries that might help you to like understand like those pitfalls, whatever they might be.
Yeah, like one thing I've noticed, like people who are totally new to Noir, like I've seen people building, age verification circuits, and you just do an assertion in the circuit that your year of birth is greater than the current year, which is also like an input. But yeah, that it's just proving that the prover knows a value that's like 18 higher than the current year. I don't know if it's unclear. I mean, like in my previous workshop last week, I go through this. So yeah, if that might be like an interesting watch for new people to understand the concept of prover and verifier, and like the role of what the verifier is verifying, what they should verify. But yeah, like one common, um, I mean, one thing to make sure as a verifier is to validate these public inputs. So if I'm sending this proof and this public inputs to verifier, and you just simply pass this to BB verify function, it will return true. But as a verifier, in this case, or in case of StealthNote, you also need to verify that. I think this, so this is what we made public in our circuit, and like this is the public key of, this is the Gitclaim public key of GitHub, and in StealthNote it was the JWT public key of Google. So as a verifier, when you are verifying the proof, you need to also make sure this key belongs to Google, or in this case, this key belongs to GitHub. Otherwise, the prover can, they can generate their own key pair, and then sign email and then generate proof, and then they can just produce a valid proof. The circuit itself is not checking the key belongs to Google, right? It's only checking that it's a valid signature with the key one public key. So in general, it's the role of the verifier to validate every public input is valid. Yeah, that's one bit. Um, yeah, one important bit.
Yeah, awesome. I think just due to time constraints, since we have a show and tell right after this,
Yeah,
we'll end this here. So Leo
yeah.
is available in the Discord to answer questions. If you guys have specific questions around StealthNote, Gitclaim, or some of the stuff he covered in the workshops, and then these will also be posted. The recordings will be posted in the Notion and on YouTube. And on YouTube, we actually have a playlist. So if you just want to watch all of the workshops from the beginning, you're in the build weeks or whatever, just play them on 2x or 3x speed in the YouTube playlist. But cool. Thank you, Salil, for joining us and for going through this. I think it'll be very helpful to beginners. And I think StealthNote and Gitclaim are a good place to start if you're interested in either of those use cases around ZK email or Noir JWT. But cool. Thanks, guys. See you in the next workshops or sessions. Bye, everyone.
Thank you. Bye.